Hey everyone, welcome back to another Linux and DevOps tutorial. In this video, we are diving deep into two essential concepts, container and orchestration. If you're a system administrator or a developer, this is something you must understand to work with a modern infrastructure and cloud native tools like Kubernetes. Let's move to the next slide. Before we understand why containers are so useful, let's first ask what exactly is a container? A container is a lightweight portable box that includes your application code, the library it needs, its setting and dependency, and a runtime environment, all bundled into one package that can run anywhere on laptop, server, or in a cloud. The Tupperware analogy, think of your application as a food and the container as a Tupperware box. No matter where you take it, home, office, or a picnic, your food stay fresh and same. So just like a food in a container, your app behaves the same no matter where you run it. This analogy make it easy to understand why containers are so powerful in software development. Let's look at why containers are awesome. They run reliable in any environment. They give a consistent deployment experience and they are isolated, which means they don't mess with other apps on your system. Whether you are building, testing, or deploying, you want your code to behave the same everywhere, and container just do that. Same code, same configuration, same behavior everywhere. If your app breaks when you move it from one system to another, container can fix that. Let's move to the next slide. Let's say a new developer joins your team. They are excited to start, but before they can write a single line of code, they have to set up everything on their laptop. That means manually installing things like database backend, web server, messaging queue, libraries, and other tools. And it's not just about installing, it's about getting the right version and configuring everything properly. This can take hours or even days, and often it still does not match what's running in production. That's when you hear the famous phrase, it works on my machine but not on yours or in production. Container solves this. Now imagine instead of doing all that manually, you just run one command docker compose up and boom, everything is up and running. The database, app, the web server all ready to go. Container let us share the exact same environment with the whole team, make sure development, testing, and productions are identical, set up everything in a minute, not days, avoid conflicts with other software or your computer. It's like giving every developer a pre-packed toolbox. Everyone gets the same tool, neatly organized and ready to use, no matter what kind of laptop or system they use. This is why the container are a game changer. They make life easier for a developer and a system admin by making environment simple, fast, and consistent. Let's move to the next slide. Now let's take a look at how a real-world application architecture is structured. This diagram shows a simplified yet powerful example of a modern web app setup, the kind you might work with every day as a developer or a system admin. Let's break this down. The architecture includes four main components that are common across most full stack application: web server, backend, database, and messaging queue. The web server acts as the entry point. It handles the incoming HTTP request from user, like when someone visit a web page. Popular choice here are Nginx and Apache. Both are powerful and flexible. Think of this like a receptionist at an office. It receives all incoming calls and route them to the right person. Next is backend app. This usually written in something like node.js or a Python. This is logic layer. It processes the request, interact with the database, and prepares the data before sending it back. If a user wants to view their profile, The backend will fetch their info from the database and send it through a web server to their browser. Next is database, which stores the actual data, user profile, transaction, product listing, and so on. Common relational database here are MySQL and PostgreSQL. These systems allow you to perform powerful queries efficiently. Next is messaging queue. For more scalable or event-driven system, we add a message queue like RabbitMQ or Kafka. This helps to handle the background task or distribute the work across the service. Sending an email after a user sign up, no need to delay the response to the user while the email sends, just push it to the queue. Here is how it all flows. A user send a request via the browser, it hit to the web server, and the web server forward it to the backend app, and the backend may query the database or enqueue the background task. The response flows back to the user. Traditional setup problem, but there is a catch. When everything is installed directly on the host system, we run into the problems, issues like version conflicts, configuration hell, works on my machine syndrome, dependency nightmares. Imagine your backend needs Node 18, but your coworker system runs Node 16. The app might crash or behave unexpectedly. With container like Docker, each component runs in its own clean and isolated environment, no more clashes or surprises. Let's take a lunchbox analogy. Think of each container as a sealed lunchbox. Everyone gets the same meal, packed exactly the same way, no mess, no mix up. Let's move to the next slide. In this slide, we are going to break down one of the biggest reasons why container, especially Docker, have completely changed how we deploy the software. Let's compare traditional setup versus the modern containerized setup. As you can see, the traditional setup, this is an old school setup. Everything Node.js, Python, MySQL, Nginx, Redis, MongoDB is installed directly on the host operating system. These services shares the system resource and that leads to the bunch of issues. Challenges includes like version conflicts. One app may need Python 3.8 and other need 2.7. Manual installation. Installing all dependency manually is the time consuming. Dependency can break each other. One library update may break multiple applications. Non-replication environment. What works on your laptop might fail on production. This was painful for system admins and a developer alike, especially when deploying across a multiple environments. Now let's see containerized setup. Enter the modern approach, containerization using the Docker. In this setup, every app and its dependency are packed into the separate container. Think of them like a self-contained units. Nginx, Node.js, MySQL, Redis, Python, each has its own environment isolated from the other. Benefits includes isolated environment, no stepping on each other toes, no version conflicts, you can run Python 2.7 and 3.8 side by side. Simple deployment, usually just one command, multiple services can run simultaneously without interfering. Docker makes this easy. Docker is the most popular tool for managing the containers. Want to run Nginx? Just run docker space run space Nginx. That's it. No downloading packages, no dependency hell. Just run the container and you are good to go. Let's take a quick analogy. Think of a traditional setup like a roommate sharing a single kitchen. Conflicts are bound to happen. Containerization is like giving each person their own mini kitchen, fully equipped and isolated, no more fights over the oven. Containerized setup does not just make a deployment cleaner, they make them repeatable, scalable, and portable. Whether you are working in a development or managing a production cluster, this shift is a game changer. Let's move to the next slide. All right, let's break down how Docker works under the hood. This slide explains the core Docker architecture in a simple way. At the center of it all is the Docker engine, which run on the host operating system. It's what actually built and manages the container. Instead of running a separate operating system like virtual machine do, Docker container shares the same Linux kernel from the host. This is a key reason why Docker is so lightful. On the right, you can see the key feature of Docker engine. It uses a client server model where you send a command and the engine executes them. It uses namespace isolation to make sure containers don't interfere with each other, and it uses control groups or C group to manage system resources like CPU and memory for each container. Now let's talk about shared kernel section on the left. There is no full OS inside each container. That's a huge win. Containers are lightweight and start in just a few seconds, and because there is no OS overhead, they use a way less system resources. All of this is possible because they share the Linux kernel of the host OS shown in the middle. The host system also handles the security and isolation, so containers stay sandboxed and safe. And finally, at the bottom right, you will see how Docker works consistently across all major Linux distributions, whether it's Ubuntu, Fedora, CentOS, or OpenSUSE. The same container image will run on all of them without any changes. That's the real power of Docker. Same application container work across all distribution. So to summarize, one Docker engine, multiple isolated container, and one shared kernel. Super fast, super efficient. Let's move to the next slide. Now let's look at how the shared kernel concept works visually. Here in the diagram, we got three different containers, each running its own app and dependency. One running a web server like Nginx, another is running a node.js app with npm packages, and the third is running PostgreSQL database. But notice they all connect down to the same Linux kernel provided by the host system. This shared kernel model is what makes kernel so powerful. There is no need to boot up a full OS inside each container. Only the necessary binaries and libraries are included. To make it even easier to understand, think of it like a browser tab. Imagine the Linux kernel is your browser, say Chrome or Firefox, and each container is like an open tab. You might have Gmail in one tab, YouTube in another, GitHub in next. They are all isolated from each other, but they share the browser core engine underneath. So each tab means a container runs separately, but they don't need a new browser for each one. That's exactly how containers work. Isolated environment sharing the same kernel. And this leads to the three key benefits: super efficient, lightning fast, and secure isolation. Super efficient, no need to run multiple OS like VMs. Lightning fast, container starts in second while the VMs take minutes. Secure isolation, thanks to the namespace isolation, container cannot see each other process. Takeaway here is containers are like browser tab. They are fast, lightning, and secure isolated, all while sharing the same kernel. Let's move to the next slide. This is very common question. Can Docker run Windows container on Linux? And the answer is no, not directly. Here is why. Container shares the host kernel. Windows container needs the Windows kernel. Linux container needs the Linux kernel. So if your host OS is Linux, there is no way to directly run a Windows container because the underlying kernel is incompatible. Now if you are following along with the slide, take a look at the diagram here. It shows the two scenarios. One, on the left side, Linux container work perfectly with a Linux kernel. On the right side, Windows container fail to run because the Linux host cannot provide the required Windows kernel. Just remember, think of the container like lightweight virtual machines that rely on the host OS. If the host is Linux, you cannot load a Windows kernel into it. It's like trying to run Xbox games on a PlayStation. But there are some workaround. WSL2 Windows Subsystem for Linux lets you to run a Linux container on a Windows virtual machine, let you run any OS in isolation. Docker Desktop handles the VM magic behind the scene for Mac OS and Windows. Let's see an example. Running a Linux container, Docker run Ubuntu. Works on Linux host, works on Mac OS with Docker Desktop, works on Windows with WSL2. Running a Windows container, Docker run Microsoft slash Windows Server Core does not work on Linux host, does not work on Mac OS, works only on Windows host. To summarize, Windows container need Windows, Linux container are much more portable across a platform. Let's move to the next slide. Let's take a moment to understand the difference between container and a virtual machine visually. On the left, we have the container architecture. Container shares the host OS and run the top of the Docker engine. They are lightweight, measured in MB, boot up in second, use fewer resources, and provide process level isolation. Perfect for running multiple microservices with minimal overhead. On the right side, we have virtual machine. Each machine has a full blown OS and runs on hypervisor. They are heavy, often GB in size, take minutes to boot, consume more CPU and RAM, but offer full hardware level isolation, make them ideally for strong security and legacy app support. So, what are the best suited for? Virtual machines are great for running a different OS type like Windows, Linux host, hosting legacy application, use cases needing a strong security isolation, and the container are ideal for microservices architecture, cloud native development, CI/CD pipeline in DevOps workflow. So the key takeaway is container are fast and efficient, VM are more isolated and flexible with OS type. They both have their place, and in modern infrastructure, they often complement each other. But for microservices and cloud native apps, containers are preferred. Let's move to the next slide. All right, let's talk about one of the most common point of confusion in Docker, container versus image. An image is a blueprint. It's read only and it contains everything your app needs, the code, dependency, runtime, even the base OS. Think of image like Nginx colon latest, Ubuntu colon 20, or Python 3.9. These are stored in the registry like Docker Hub and they never change once built. You can pull an image using Docker pull followed by the image name. A container, on the other hand, is running the instance of the image when you run docker run -d nginx. Docker takes the image, layers a writable file system on top of it, sets up a networking, mounts point, and spin it up as a container, like a live functioning application. You can list running containers using Docker PS. The key difference is image is read only, container is read write. Image is just a blueprint, container is a live application. Images are immutable, containers are stateful and controllable. You can start, stop, or delete them. In real world analogy, an image is like an ISO file, static and unchanging. A container is like operating system running from that ISO, dynamic and interactive. That's the core difference. Once built, the other runs. Let's move to the next slide. Let's break down why containers are a game changer, not just for developers, but also for system administrator. For developers, quick environment setup, imagine spinning up your entire app stack, web server, database, backend with a single command, Docker compose up. No more it works on my machine drama, everyone runs the same setup. Identical environment. With containers, your dev, staging, prod environments behave the same. That means fewer surprises during the deployment. Version control dependency. You can log the version directly in your Docker file or a docker compose.yaml file. Want Node.js 14, Python 3.9, and MySQL 5.7? Just declare them. For system administrator, better resource utilization. Containers are lightweight. They share the host OS kernel, so they use less memory and CPU compared to full-blown virtual machines. That means more apps on fewer server, cost efficient and scalable. Application isolation. Each app runs in its own container, so if app A crashes or gets compromised, app B and C are safe. This isolation boosts security and stability. Easy ops management. Container simplifies monitoring, scaling, and rollbacks. Need to scale out, just spin up more containers. Made a mistake in deployment, roll back in a second. For a quick example, let's say your dev team builds a web app using Node.js and MongoDB. Using Docker Compose, the entire stack can share with ops in one file. Ops can then deploy it across environments, same configuration, same behavior, and scale it based on the traffic with zero friction. It's a win-win. Happy developer, happy system administrator is equals to ultimately better products for the user. Let's move to the next slide. So far we have seen how powerful containers are, but what happens when you are running the tens or even hundreds of containers across multiple machines? That's where container orchestration comes in. Let's see the challenges. Managing the container manually at a scale is a nightmare. It's error prone. If a container fails, you need to react fast. Networking between services can get very complex, and workload might not be evenly distributed across machines. What orchestration solves? A container orchestration automates all of that. It handles container lifecycle management, start, stop, restart, reschedule, self-healing. If a container crash, it gets restarted automatically. Service discovery and load balancing, so services can find each other and the traffic get distributed evenly. Dynamic scaling, spin up more containers when demand increase and scale down when it drops. How it works? At the top, you have got your orchestration like Kubernetes or a Docker Swarm. It manages cluster of nodes, node 1, node 2, node 3. Each node can run multiple types of container, front-end container for deploying UI service, backend container for scaling APIs, database container with auto restart and failover, plus it handles networking, load balancing, and rolling updates, all in a seamless and automated way. Let's take a quick example. Let's say your e-commerce app has a front-end, backend, and a database. With orchestration, you define your deployment in a YAML file. The orchestration ensures the front end runs on node 1, the backend scales across the node 2 and node 3 based on the traffic, and the database gets restarted automatically if it crashes. And yes, it's also distributed the network traffic using load balancing. You don't have to log into the server and fix anything manually. Orchestration brings reliability, scalability, and peace of mind for both developer and system admins. So when your apps grow, orchestration ensures your infrastructure scales with it automatically. Let's move to the next slide. Let's look at some of the most popular tools used to orchestrate container at scale. There are three major players in this space. Docker Swarm, simple but limited. Swarm is great if you're already using Docker and want something lightweight. It has native Docker CLI integration and it's super easy to set up, but it's not great for large scale production. It lacks advanced features like custom scheduling and full auto scaling. Ideal for small teams or quick MVPs like minimal viable product. Adoption good for small project, but adoption has dropped as Kubernetes gains the dominance. Next is Kubernetes. Kubernetes is most widely adopted orchestration platform. It's extremely powerful, support autoscaling, self-healing, service discovery, load balancing, and massive plugin ecosystem. Backed by the Cloud Native Computing Foundation (CNCF) and major cloud provider like AWS, GCP, and Azure. Market adoption clearly the leader. It's the go-to for most real-world production setup today. Next is Apache Mesos, complex but flexible. Mesos is a powerful distributed system kernel, not just for the container. It's known for high scalability and support for mixed workloads, container, big data, and even legacy apps. But it has the most complex setup and the stepper operation cost, mostly used in large enterprise with custom infrastructure needs. Adoption is niche, powerful but less commonly chosen compared to the Kubernetes. And the summary is who should use what? Docker Swarm, simple project, dev or test or smaller deployments. Next is Kubernetes. Most teams uses production workload, cloud native apps, scaling needs. And the Apache Mesos enterprise with custom or hybrid workload including a big data. There are other tools like Nomad by HashiCorp or Amazon ECS, but Kubernetes remains the gold standard in open source orchestration. If you are starting fresh or scaling up, learn Kubernetes. It's complex at first, but gives you the control and flexibility to run a production grade containerized application like a pro. Let's move to the next slide. In this slide, let's explore the real power of Kubernetes, not just in theory, but how it actually works under the hood. Kubernetes lets you deploy your entire application stack as orchestrated containers, meaning your apps are automatically scaled, managed, healed, and discovered all in real time. Let's look at a diagram first. At the top, we have Kubernetes control plane, which includes the API server, scheduler, controllers, and etcd. This is the brain of your cluster. Then we have a multiple nodes, the actual machine, physical or virtual, where container runs. Node 1, Node 2. Each node runs kubelet agent that talks to the control plane. Node 1, we have the front end and back end pods. Node 2, we are running a database and caching pods. The load balancer sits between the user and the Kubernetes cluster, distributing the traffic intelligently to the right pods. Front end pods run UI framework like React and Angular. Kubernetes autoscales it. Here we have the three replicas running for high availability. Backend pod handles the business logic, Node.js, Python, Go, etc. Load balance with 5 replicas to handle the API traffic. Database pod manages the persistent storage like PostgreSQL or MongoDB. Uses a stateful set to maintain the data consistency even if the pod restart. Caching pod run fast access tool like Redis or Memcache. Built with self-healing in mind, Kubernetes ensures at least 2 replicas are always active. Let's see the key feature. Scaling automatically increase or decrease the pod based on the CPU usage or custom metrics. Load balancing spread incoming request across all available pods. Self-healing automatically replace failed containers. No need for manual restart. Service discovery Kubernetes handles the internal DNS so that the service can easily talk to each other. This is why Kubernetes is the backbone of modern DevOps. It removes the pain of manual scaling, recovery, and service wiring. So you can focus on building the great application. So let's move on to the next slide. That's it for this tutorial. In the upcoming series, we will show you how to deploy the application using Kubernetes, managing the pod, services, and deployments. And also, please check out our previous video where we have shown you how to install Minikube on Linux. Stay tuned and don't forget to like, subscribe, and hit the bell icon for more real world Linux and Kubernetes tutorial. Thanks for watching. See you in the next one.